Okay, so potential energy, kinetic energy, and total mechanical energy. Lots of stuff. So potential energy. We're going to talk about gravitational potential energy first, and that's all based on mass and height. So potential energy based to gravity is mass times g times height. With on Earth g being 9.8, mass should be in kilograms, height should be in meters, and that's how we can solve for potential energy. So if we look at somebody on a swing, as they swing higher, they have more height, which means their potential energy is going to be greater than it is here. And here, the potential energy of the higher swinger is going to be greater than here. So height controls potential energy, especially when the object, in this case, this person, isn't changing mass. Now let's look at potential energy change. So at the top, we're at 50, okay? At the bottom, we're at 0. So at E and F, we're also going to be at potential energy of 0, regardless of the path we take, if we go down the stairs, down the slope, or drop straight down. But now, in between, it's going to be 1, 2, 3, 4 different steps. So it's going to be 40 joules here, 30 joules of energy as our height decreases, 20, then 10, then 0. 0 at the bottom, 0 at the bottom. So irregardless of the path, potential energy, if we drop from the same height and end at the same spot, will be the same. Again, irregardless of path. Another type of potential energy is elastic potential energy. So like, let's say we have this little gun here and it has compressed springs that shoot the dart, right? When we push the dart into the gun, we compress the spring. And by doing that, our spring has potential energy. That potential energy then will propel out and shoot the dart. So potential energy of a spring is 1/2 or 0.5 times K. K is called the spring constant, which is something will be given to you or you'll have to solve for. And then X is how far the spring is compressed, and that is squared. So 1/2 kx squared, and that's potential energy of a spring. Here's an example of a problem with potential energy. A cart is loaded with a brick and pulled at a constant speed along an incline to the height, all right, of a seat top. If the mass of the cart is 3 kilograms and the height is 0.45 meters, then what is the potential energy of the loaded cart at the height of the seat top? So from this height right here, right? Do it now. All right, so we are taking this cart and we're pulling it up this slope. Now, the big thing here to understand is that potential energy is mass times g times height. Now, our mass of our cart is 3 kilograms. G is the acceleration due to gravity, so it's 9.8 meters per second squared. And then m, or h, is our height in meters that we're coming up, all right, so 0.45. And then it's just a matter of multiplying all these answers. So 3 times 9.8 times 0.45, and I get 13.23. And we're talking energy, so it's joules. 13.23 joules. And that's how much energy we give it when we raise that thing up. Okay, so now we're taking the same situation, and we got a force of 14.7 newtons. We're going to drag the loaded cart from the previous question along the inclined distance of 0.9 meters. How much work is then done on the loaded cart? Do it now. All right, so same setup, our 3 kilogram mass, but now we're pulling it with a force of 14.7. That's the tension force on the string up this slope, a distance of 0.90 meters. So we want to do work. Work is force times distance. So our force is 14.7 newtons, and our distance is 0.9 meters. So this is newtons. This is meters. So we're going to get joules for our answer, 14.7 times 0.9. 13.23 joules, which is the same as potential energy. So here's my point. Lifting it up this high or dragging it here, we're putting the same amount of energy into it. This is through work, that's through potential energy. So work and potential energy in this case are the same thing. And then we have kinetic energy. Kinetic energy, excuse me, is the energy of motion. An object that has motion, whether it's vertical or horizontal, has kinetic energy. And kinetic energy equation is 1/2 times mass times velocity squared, or speed squared. So 1/2 mv squared. That is kinetic energy. So let's do a sample of this. We want to find the kinetic energy of a 625 kilogram roller coaster car that is moving with the speed of 18.3 meters per second. Do it now. All right, so our 625 kilogram cart's moving with the velocity of 18.3 meters per second, and we want to find kinetic energy. Kinetic energy is 1/2 mass times velocity squared. So 1/2 625 times 18.3 squared. And we math it out. 1/2 times 625 times 18.3 squared gives me a kinetic energy. It's a pretty big number. We're just going to round it to 3 sig figs, 105,000 joules. And that's the kinetic energy we have in this cart. So big cart, big velocity, especially when we square it. Boom, a lot of joules of energy. Missy DeWater, former platform diver for the circus, has a kinetic energy of 12,000 joules just prior to hitting the bucket of water. If Missy's mass is 40 kilograms, then what is her speed? Do it now. All right, so we got our jumper with a mass of 40 kilograms going all the way down trying to hit this tub of water. Right before it hits the water, it has 12,000 joules of kinetic energy. How fast is our diver going? Well, let's look at the equation. Kinetic energy is 1/2 mass times velocity squared. So let's substitute in. Kinetic energy is 12,000. 1/2. Our mass is 40 v squared. So I'm going to do a step here. I'm going to take 1/2 times 40, which is 20. So 20 v squared is equal to 12,000. Divide both sides by 20. I'm going to do that one in my head. So 12,000 divided by 20 is 600. And then to solve for v, I take the square root of both sides. So I take the square root of 600. And I get 24.5 meters per second. So that's how fast the diver is right before they strike the water. So using the equation, just solving for v. Don't forget to take the square root. That's where most people make the mistake. Now, the term mechanical energy can be either kinetic or potential. So an example would be, let's say a person pulls back on a bow. The bow possesses mechanical energy because it's in the form of potential energy. It's elastic because we're stretching, right? We're stretching this. It's not a spring in this case, but we're still stretching the string. So mechanical energy in the form of elastic potential. Mechanical energy has the ability to do work. So let's look at one of these demolition machines with a wrecking ball. And the wrecking ball has potential energy. As the wrecking ball releases, potential energy as it drops is converted into kinetic energy. So potential converted into kinetic. That kinetic energy hits the building. Remember, work is force times distance. So here it takes that energy and applies a force, or is doing work, to the building. And then the building, of course, gets demolished. So mechanical energy can be converted into work. Other examples of that, we have a hammer. And when we move the hammer, we are using kinetic energy, right, to give it motion, 1/2 mv squared. So the faster we swing the hammer, the more energy we have. That energy then will do work on the nail by applying a force over the distance we move the hammer, hopefully to get the nail into the board. Bowling, the ball has kinetic energy, and then it hits and applies the energy to the pins. Now, we're doing work, kind of. We're applying a force to the pins, but really what we're doing is we're transferring the energy from the ball to the pins, because now the pins have no kinetic energy, but then the ball gives its kinetic energy to the pins. So that kinetic energy gets sent to the pins. But again, it's still mechanical energy. Compressed springs in a gun can apply a force to do work to the dart. High-speed winds, if we have wind turbines, as they turn the turbines, it does work. And by applying a force to these turbines, that work then can be used to make electricity, which we'll talk about hopefully at some point here by the end of the semester. So total mechanical energy, kinetic energy plus potential. It can be gravitational or spring potential plus kinetic. That's total mechanical energy. So here we go. Kinetic energy, 0. Potential energy, 50,000 joules. As it starts to go down, potential energy decreases, but then the object starts to gain speed, so kinetic energy increases. But at the end, potential plus kinetic will equal potential plus kinetic at the start, because energy is conserved. So if we have 50,000, this will equal 50,000. Down here at the bottom, our potential is lower, but we're going faster, so our kinetic's higher. Added together also equals 50,000. Then we hit the ski jump and go into the air. Once we get the ski jump here, we're at the same height as we were here. If we're at the same height, we have the same potential energy, which means we'll also have the same kinetic energy, because total energy, again, is conserved. So that will equal 50,000. Then at the bottom, all of our potential energy has been converted to kinetic. But again, total equals total.